Today we're going to take a look at forces and free body diagrams. Alright, so defining force. A force is a push or pull that has the ability to cause a change in motion. So the unit for force is the Newton. It is defined as the force needed to make a 1 kilogram object accelerate by 1 meters per second squared. Therefore, force is equal to mass times acceleration. Force is a vector, meaning you have to specify direction. Up is positive, down is negative, left is negative, right is positive. And if a question ever asks you what's the magnitude of the force, that means you don't need to calculate the direction. You don't need to specify if it's positive or negative or up, down, left, or right. Forces require two objects, but is not necessarily in contact. So for example, a tow truck exerts a net force of 205,500 newtons on a car, accelerating at 5 meters per second square. The mass of the car is... So we're going to first write down the equation, F equals ma, and what you'll notice is that F, the net force, is 205,500. So that's what we're going to put instead of F. M is what we're looking for. We're looking for the mass of the car. A is the acceleration, which is highlighted right here in green. So we put that all together, and we get 205,500 is equal to m times 5. So all we have to do now to get rid of the 5 is divide it on both sides, and we have pretty much solved for m. Once you plug that in the calculator, you get your answer, which is 41,100. So there are two types of forces. There are contact forces and there's field force. Now they're both measured in newtons. The main difference is that contact forces require physical contact, whereas field force can be applied from a distance and does not require physical contact. Examples of contact forces are tension, normal force, air resistance, or even a good old push or pull. Examples of field forces include electric force, magnetic force, gravitational force. These are all examples of field force. Now, gravitational force is probably the most common, and it's the one that you're experiencing right now. You do not need to be connected to the earth to experience a gravitational force. If you jump, you are no longer connected to the earth, but the earth still pulls you towards its center. So that's a great example of a field force. Gravitational force, commonly known as weight. So we do not want to confuse mass and weight. They're two completely different things. They're very related to each other, but they're two different things. So in this equation, it's basically the F equals ma equation, except A is a constant. Fg represents gravitational force, m represents mass, usually in kilograms, and g is the acceleration due to gravity. Now, most of our problems are going to be on Earth, so g is going to be negative 9.8. But you will get some problems where we'll tell you we're on Mars or we're somewhere else, and we'll give you the gravity in that case. Here's an example. Heaviest gorilla ever in captivity was a male in the San Antonio Zoo. At one time, he weighed 201,420 newtons. What was his mass? So they gave us F, which is 201,420, and they don't have to give us G because we're assuming we're on Earth. Well, we're obviously on Earth because San Antonio is on planet Earth. So G is going to be negative 9.8. So all I have to do to find the mass is divide by G. As you can see here, we have the negative 201,420 divided by negative 9.8. Our mass is 205.53. So what you'll notice is that I made his weight negative. That's because weight acts in the downward direction. Remember, we said that force is a vector. So the fact that weight points down means that I have to report it as a negative number. Mass ain't weight. Mass is measured in kilograms. Weight is measured in newtons. Mass never changes, no matter what planet you're on, where you are. If you have the same amount of stuff, same amount of atoms, then you always have the same mass. I know we're used to saying that something weighs 50 kilograms, but we try, especially in this physics class, to say that something has a mass of 50 kilograms. Weight is in newtons. So mass is how much substance you're made out of, versus weight is how much force you is going down because of your mass. So weight can change depending on gravity. More gravity means more weight if you're having the same mass. So here's an example. Compared to its weight and mass on Earth, an object on Jupiter will do what? Well, Jupiter has a greater force of gravity per kilogram than Earth, so therefore the object will weigh more on Jupiter, but the mass will remain the same. X and Y components of force. We have the horizontal component and the vertical component. And just like when we did 2D kinematics, you kind of have to deal with them separately. So the way you get Fx is to get the original force times cosine of the angle that the force is applied, whereas Fy is the original force F times sine of the angle at which that force was applied. When we're talking about the x direction, we're talking about left and right, where left is negative and right is positive. You can only add x components with other x components. If something is being pulled across the floor, or is just moving horizontally in general, that means that your vertical components have basically canceled each other out, usually with a normal force or something like that. You can only add y components with other y components, keeping in mind that up is positive and down is negative. Here's an example. Student pulls a box of rocks on a frictionless horizontal surface with a force of 55 newtons at an angle 25 degrees above the horizontal. If the mass of the box and rocks is 50 kilograms, what is the acceleration of the box? So the box can only move in the horizontal direction because we're pulling it across the floor. Therefore, we need the horizontal component of the force. We could get the vertical component of the force if we wanted to know what the normal force is, or basically just for more information. But the box is not going to move up or down, so I'm only concerned with the horizontal component. So Fx is equal to F cosine theta, which would be the 55 newtons of force times cosine of 25 degrees. So that means, horizontally speaking, I'm pulling with a force of 49.85. So now we're going to use F equals ma to get the acceleration. F, 49.85, equals 50 times a. So if I want a by itself, I'm going to divide both sides by 50, and I get a equals 0.9969. So we're not going to use that many decimal places, and even if I round it all the way to 2 decimal places, I get 1.00. So it's approximately 1 meter per second squared. Now let's take a look at net force. It's defined as the sum of all forces acting on an object. Remember, force is a vector, so we have to add them like vectors. F net is going to be equal to MA, which is basically what F equals MA is. Since we're talking specifically about net force, you have to add all the forces together before you can apply the MA. An object is in physical equilibrium if F net is equal to 0. So if F net is equal to 0, right, then acceleration is 0. Because you're not going to have 0 mass if you're talking about an object. So when in physical equilibrium, acceleration is 0, which means either velocity is constant or the object is at rest. If your problem says any of those two things, that means your F net is 0. Sum of all forces will be 0. So when trying to determine net force, we often start off with a free body diagram. So we're going to learn a little bit more about that. Now, just because F net is 0 does not mean that there's no forces acting on the object. For example, I'm going to assume you're sitting down or laying down and you have 0 acceleration. That does not mean that gravity is not acting on you. It just means that whatever you're sitting on or laying on is providing an equal and opposite force, keeping you at the same position. So in other words, your force is going down because of your weight is canceled out by the normal force going up because of what you're in contact with, giving you a net force of 0. Now we have two types of forces in free body diagrams. We have the applied force and we have some natural forces. So an applied force is a force that affects an object that comes from something other than the object. So this could be a gravitational force, this could be a contact force, this could be something experiencing a force because of an electrical field. It's an applied force if it's coming from outside the object. Pulled by a string, pushed, lifted, that kind of stuff. Now we have natural forces that are going to occur naturally. You have gravitational force, which is always down. You have the normal force, which is always perpendicular to the surface. And you have friction, which is always in the opposite direction of the motion. Friction can come in the form of two surfaces rubbing against each other, or it could be air resistance, where air particles are pushing against whatever direction the object is moving. But friction is always in the opposite direction, no matter what type of friction you're talking about. So here's an example. Create a free body diagram. A box is being pushed up a frictionless plane. Now this is what it might look like in real life. There's a box, it's being pushed. But if I'm doing a free body diagram, I'm going to isolate that box and I'm going to use arrows to represent all external and natural forces, all the applied forces, all the natural forces. So the box, the push is represented by F. The weight is represented by that arrow going down, which is mg. And the normal force is the force that the slope is exerting on the box. And that's your free body diagram. Here's an example. Toy car is being pushed to the right along a carpeted floor at a constant velocity. The applied force needed to maintain the car's velocity is 4 newtons. What is the force of friction acting on the toy car? So that's what our free body diagram would look like. Now the weight and the normal force, they're going to cancel each other out because we're pulling it on the floor. It's not going up or down. So F net is going to be equal to the applied force plus the frictional force. Since F net is 0, because the car's velocity is the same, it's constant, FA plus FF is going to be equal to 0, which means frictional force is equal to negative FA, which is negative